Okay, so this will be an introductory tutorial to the topic of machine learning. And I should start by giving credit to Talia Rokem, who wrote a lot of this tutorial, and I've been using and reusing it for a while. And the goal of this tutorial is explicitly not to give you a broad range of exposure to machine learning, because machine learning is a pretty broad field of activity with lots of different subtopics and really interesting avenues, but rather to give you some broad principles. Hopefully, throughout this tutorial, I'll make you know enough to just enough to be dangerous, and then I'll pull you back to being slightly less dangerous towards the end. Let's see if we can achieve both of those things at the same time. Hopefully, you're not too dangerous. So just some preliminary things here. There's not a lot to say about this preliminary notebook. So first of all, I am inside of the curriculum folder under this Rokem ML, and then I've started, there's a series of notebooks here, and we'll try to go through most of these, although we might not get through all of them. Just general principles, the notebooks have various pieces of code that you can run along with me, and you can change various things. If variables or names are in uppercase in particular, those are things where you can play and see what happens if you go from 30 to 300, for example. There's some code in here in the support folder that we will import from all kinds of helper functions. So when you see that, don't be alarmed. The code is in here. All the software is on the hub, so we don't need to belabor that. But if you want to run this elsewhere later, then that all this stuff is also online, and there's instructions here for how to set up a new environment to use that. And we'll be using some data, so I'll start introducing the data that we'll use first here, which is data from the Autism Brain Imaging Data Exchange ABIDE in its second iteration, so ABIDE 2. This data was processed and shared by Bethlehem et al. In a paper that they wrote a few years ago. And we're using that table of data that we've slightly augmented and kind of organized. And that data is stored inside of the shared folder. There's everyone that this is also a kind of useful thing for next week to think about. There's a shared folder in your home directory in the hub, and that shared folder has some data sets, including this data set. And that's where I'm going to be reading it from here using pandas. And so what the data frame roughly has is it has data from 1,004 subjects in the ABIDE 2. The first few columns here, the first 6 columns here are descriptors of this data. So first of all, the Autism Brain Imaging Data Exchange was a large project to collect data from people with autism and match controls over multiple different sites and share that data jointly. It's a little similar to what you just saw about Enigma. That data is all shared openly to anyone also. So that's how we can get this data and use it really, really easily because it's openly available. And this particular processing of the data includes then the site from which this was collected, the subject identifier, the age of the individual to a ridiculous precision. Age residuals, we'll come back to the age residuals in a little bit. The sex and then the group. If it doesn't say here, yes, here. 1 is a person who has autism, 2 is controls. Sex, I simply do not remember. This is just a warning for everyone. If you want a sex column, maybe you should call that column is male and have 0s and 1s in there instead of sex with 1 and 2, because I don't know what this is. And then to the right of this are about 1,440 columns of FreeSurfer processes. So this has been processed through the FreeSurfer pipeline, and these are properties of various regions of interest defined by FreeSurfer. So for example, this is area left V1, and I believe the first one is the area of the region, and then there's actually 4 different groups of variables The details are actually not too important, except to say these are data that have been extracted from brain images and are now in tabular format. As an aside, this kind of data format is sometimes referred to as tidy data. Has anyone here heard of tidy data? Like as a technical term? Tidy data is its technical term that means that the data is organized as observations on the rows and then features on the columns. This makes it particularly amenable to a lot of the things that we'll do later in the tutorial. It has a very specific technical meaning. There's a paper by Hadley Wickham called, the title of which is Tidy Data, that describes in a lot more detail what tidy data actually means. There's also kind of a whole part of computer databases where this is also known as the third normal form. So this is also, there's a real technical definition of this, but roughly speaking, it means that there are observations on the rows and then features on the columns, or different variables on the columns. And that makes it really amenable to the kind of analysis that we'll do here. Yeah, here's the full reference to the paper from which this data came. And so on we go. Let's start with some machine learning concepts. So we'll start here by importing some things that we'll use. We will use NumPy for numerical computing, pandas. We've all already seen that one read their data for us. Matplotlib for visualization, and we will also use a library called Seaborn for visualization. So you'll see a little bit of intermingling of other things that are not machine learning, like visualization and data analysis more generally. Well, so we're talking about machine learning. This might be a good point at which to define what machine learning is. Machine learning is the field of science and engineering that seeks to build systems that are capable of learning from experience. The idea is that these are systems that can see data and then adjust their behavior based on the data that they are observing. This is really, really broad and encompasses a lot of different things. But as you'll see later on, this also, to some degree at least, defines the way that we approach philosophically what we're doing. We're doing data analysis in contrast to traditional inference, which focuses perhaps on specifying the parameters of some model and then testing hypotheses about the data. For example, is this parameter different in this group than that group? The focus much more here is on the goal of predicting some unseen data. So we're trying to learn from some data, and then we're trying to make accurate predictions about some other data that we haven't seen yet, and that will keep coming back. And that gives us really nice objective measures for whether or not we're doing what we want to do well. Where inference is a little bit more slippery and tricky. Are we testing the right hypotheses? Is a p-value a useful thing to look at in the first place? Those kinds of questions here. We're predicting, and if we're predicting well, accurately, if we're predicting more accurately doing one thing than doing another thing, then that's better in kind of the way that we define this. Broadly, and you can read a lot of papers about this. Tal actually wrote a great paper that I think had a lot of impact on the field about why he and his co-author believed psychology should adopt this predictive thinking. Okay, but let's start digging into this definition. I've talked about something very abstract in general. We see some data and we change the behavior of the system based on this data, and something about prediction. It might be helpful to give some concrete examples and start focusing on distinctions that we make within machine learning. So one kind of broad distinction that we make is between supervised learning versus unsupervised learning. Broadly speaking, supervised learning is the setting where we have a label attached to every one of our observations. For example, in the case of the Abai data set, that could be whether that person was diagnosed with autism or not. That's a kind of label. Another kind of label that we have there is the age of every individual. That could also be a label. Those are different kinds of labels. One is a discrete yes or no kind of thing, and the other is a continuous one. And in the supervised learning setting, we are trying to learn the relationship between that label and a set of observations. For example, those brain measurements. and in a supervised fashion. What does that mean? The algorithm that is trying to learn, the system that is trying to learn something from the data has access both to the observations, the brain data, and to the labels at the same time. And it can adjust its behavior based on matching between these brain data and the observed label. In contrast, an unsupervised learning system might not have a label to go on. It would only have, for example, the brain data. One example that we might see a little bit later in the tutorial is, what if we knew that all these people had autism? We looked only at the people who were diagnosed with autism, and we looked at their brain data, and we thought, well, are there subtypes, neural subtypes of autism? Right? In that case, we don't know a priori. We don't have labels that tell us this person is of this subtype and this other person is not of that subtype. Rather, we're trying to do something unsupervised without this label to see whether there's any structure in the data that merits the conclusion that there are, in fact, subtypes within this data. We're trying to parse apart the data in an unsupervised fashion. So here's some examples of supervised learning problems. The first of which we'll do later, which is predicting people's chronological age from structural brain measurements. Another kind of supervised learning is determining whether or not an incoming email is spam. That's a popular one, which my email is doing terribly these days. Predicting a person's rating. I get really important emails sent to spam. It's really ridiculous. Predicting a person's rating of a particular movie based on their ratings of other movies. Also a kind of supervised learning problem, because in this case, we might have maybe some labels on some of the data, but then not have labels on others that we're trying to fill in. And diagnosing schizophrenia based on genetic markers. All of these cases, we can use some ground truth where we know the label in order to train the data, although each one of these has some subtleties and differences. We'll come back to unsupervised learning in a little bit, but let's, within supervised learning now, focus on a distinction. I've already alluded to this distinction, which is the distinction between classification and regression. And those are broadly kind of delineated by cases in which you're trying to, where the label is a continuous measurement, like age, versus cases where the label is a label, a discrete label, like autism, no autism. Here's regression. Regression is, and this one is a relatively simple example of regression. Here in the code, we're simulating some relationship. Here is the relationship that is being simulated. So it's one label Y and one variable X and the relationship between them. And if we plot that here, then you can see the X, which we'll think of as the features, versus Y, which you think of as the label here, and some relationship between them. And that relationship just stems from the fact that we put a relationship in there. In regression, maybe our goal is to find some kind of rule that best matches this relationship, some kind of mathematical equation that best matches this. One way to do that, in this case, we know that the relationship is a linear relationship because that's what we put in here. But a pretty good first thing to do with any data is to try to fit a linear model. Linear model here would be Y equals beta 0 plus beta 1 X. So some offset and some slope on a straight line. We can achieve that using what's called ordinary least squares regression. So here is the ordinary least squares regression solution to the problem. We start by adding a column of ones to the X measurements that we have. And then and that is in order to account for the fact that there could be an offset. That's that beta 0 that in the equation, beta 0 plus beta 1x. Then we use a function from NumPy, least squares, that knows how to take a matrix X like this and Y and some other input here that is not too important, and then get back parameters W. So here are our parameter estimates. Intercept negative 0.36 and slope 0.62. And we can plot that here. So this is a regression line through this data, the best fit regression line to this data. And so that's what we do in regression. We'll see a lot more complicated manifestations of that later, but actually not a lot more complicated. Just instead of in one dimension, we'll go to like 1440 dimensions. So things will get a little interesting in that setting. But fundamentally very similar to this idea. Classification, in contrast, is a situation where we're trying to deal with data that's labeled. Here again is a simulated example. We're going to start using the package, the Python library scikit-learn. In just a minute, I'll introduce more about that. For now, we're only importing from that something called make blobs. Scikit-learn has a nice submodule called datasets that contains functions that can generate datasets. So here it's generating a blobs dataset. And these blobs. So in this case, the data is two-dimensional. So you think of this as like the table that we had before. It had 1,004 observations and 1,440 brain features. Here we have a data set that has, I believe, not sure how many rows here, maybe 100 rows, one for each point. And then each row has two columns, actually, one for the x-axis in this picture and another one for the y-axis. And we're not actually seeing the labels on either the x or the y. They're the color here is the label. So for some of these y is equal to 0, for others it's equal to 1, or maybe 1 and 2, I don't remember exactly. But we have a data that has one set of labels and then two dimensions of x. So we've gone from one dimension now to two dimensions. And then we can start thinking what we would do in order to classify this thing. Maybe one approach here would be to find a straight line through these two that neatly separates between this. This is relatively easy in this case because they're really nice, neatly separable. But usually the world is more like this, and that makes classification a little bit more interesting. And you can imagine situations where there's no good way to separate between two classes, and things get a lot more complicated. Here's one with lots of different classes. You can think about how accurately label each point here. That gets a little bit more interesting. So that's the classification setting, and we'll talk about that a little bit more later. We'll show maybe a more concrete example, but that's roughly supervised learning, the two major families of supervised learning and the classification and regression. We'll come back to those later. But before I go more deeply into supervised learning, just back to unsupervised learning. In unsupervised learning, you can imagine that instead of having y and x, we now have only x. Right? And there's roughly two broad classes of unsupervised learning. And the first we're trying to cluster. It's similar to this neural subtypes of autism kind of idea, but here much simpler. Let's imagine that we have these blobs from scikit-learn, but we don't have labels associated with this. And our task is to say, are there actual blobs in this data that are distinctly different from each other? And what are the properties of each blob? And how would we, if we got a new observation, how would we tell which of the three blobs that we discovered this falls into? So here in this case, again, looks blobby. We actually made it from a function called make blobs, so we know there are blobs in there. But of course, and here are the blobs this came from. But imagine a situation like this one. This is the ground truth of the blobs, and what you actually see is this, and that's a lot harder to deal with. So, then there's, of course, when you think about the similarity between this clustering problem and the classification problem, here on the left, we have a classification problem because we have the labels. On the right, we might have a clustering problem, which is so make groups out of it, right? So they're related to each other. Dimensionality reduction is another kind of unsupervised learning method. Sometimes they intertwine in various ways. In dimensionality reduction, broadly speaking, we start with data that has some dimensionality, and we're trying to look at the data to see whether there's a structure that lies on lower dimensionality than the dimensionality of the original data. Here's a neat example of that. Right, so this data here has two dimensions. We're plotting, in this case, it's X and Y, but you can imagine that in the unsupervised setting, X and Y are two columns of one matrix that we're trying to discover whether there's any structure in, and whether we can describe it in less than every point here could be described in less than two numbers, right? Each point here is now, as we put it here, described by two numbers. But the question is there underlying structure such that each point here could be described in less than two numbers? And that's sort of the one way of talking about dimensionality reduction in a particular data set. And so here, for example, it's pretty straightforward to see that there's a lot of variance in some direction here and not a lot of variance in the other direction. So if we ignore how far away from this main diagonal each point is, we could describe actually each point using one number, which is how far away from the lower left corner is that point, right? So we reduce the dimensionality of the data to one number for each point, where that number represents how far away are we from the lower left corner of this figure. And we're ignoring the fact that it also could deviate a little bit up or down because there's just not a lot of variance in that direction. So we're ignoring some of the features of the data in favor of giving a more concise representation of the data. And that can be beneficial in cases where that, let's say, really the underlying process that generated this data is low dimensional. It really is all about just the direction. And everything that we're seeing off this main diagonal is noise, for example. So you can think of dimensionality reduction also being a noise reduction technique in some settings. Okay, so that was a lot of kind of overview. Let's see what questions do people have so far. Okay, if no questions, then I will forge ahead. Here is again the Abide data set. And we're loading it in here, and we're looking at the 5 first rows. Again, we've seen this before. So now the next thing that I'd like to do is to turn to the scikit-learn library that we will use in this tutorial as a way to introduce machine learning using code. So in contrast to, say, using a lot of math. Scikit-learn is an excellent machine learning library. It's got a lot of things going for it. It's got a huge user community and large developer base. It's been developed for many years now. It's really, really evolved. It has excellent documentation with lots and lots of examples. You can actually read that documentation like a textbook in machine learning if you'd like. Just start from the top and work your way through. So excellent documentation, and one of the keys to its success is the fact that it has a really, really well-designed application programming interface, or API, that's really, really uniform across many different methods in machine learning. The developers of scikit-learn have been really conservative about what they include in scikit-learn, and so the methods that are in scikit-learn are really, really well-established methods. So there's nothing experimental or cutting edge in particular about methods that are implemented in scikit-learn, but the things that are implemented in scikit-learn are kind of well-worn and used, and you can rely on them. So those are the principles that have made this really successful and a good basis to build upon. Data in scikit-learn is represented similar to the way that we've represented data here, so that this tidy data thing kind of pervades into scikit-learn. We usually have what we call an X matrix. That's this matrix, big matrix with data. And then sometimes we'll have labels that are called Y. X is most often a two-dimensional matrix. I think always a two-dimensional matrix with observations on the rows, and then what we call features or different variables on the columns. And then Y is most often although not always, one-dimensional matrix or one-dimensional array in NumPy with different variables or values that correspond to the rows of the matrix. So each entry in the Y corresponds to the equivalent row in the X matrix, right? So we have for example, a label for every individual in the Y, and then a row in the X matrix that corresponds to that with the features measured in that individual, in the case of the Abide data set. So let's construct something like that out of our Abide data set. About the whole data now, including these 6 columns of kind of phenotypical data about the people, and all these free surfer columns are stored in one pandas data frame called data. Pandas data frames have a method called filter, and if you give it the keyword arg and put like and a string, then it will pull all the columns that start with that string. And neatly enough, in this data set, all the free surfer variables start with fs. So if we do that, then we get a data frame that has only the free surfer measurements. We've kind of eliminated the age and site and subject ID, those things out of this. So this is our X matrix. We will also create a set of labels here. In this case, we will be focusing on age. So we're extracting the age, and we're turning that into a NumPy array by extracting the values. Every column in a pandas data frame also happens to be a NumPy array. So you can do this and get a NumPy array with the ages. Okay. So we have xall, which is all of these variables from the free surfer measurements, and we have y, which is our age. Let's start using scikit-learn in order to do brain age prediction. So this will be an example of regression. What we're trying to do is build a system or a model that based on 1,440 numbers from a free surfer measurement, try to estimate what the age of or predict what the age of a person is. Scikit-learn, the workforce of scikit-learn are a set of classes or Python objects called estimators. This is the main application programming interface or API that you'll use in scikit-learn. These are objects that have that implement 2 classes that are really important. One is called fit, and the other is called predict. We'll see that in action in just a second. Actually, let me go to that. Let's say, so I'll come back to this paragraph here that describes all this and fit and predict. And let's actually go to the code first. So here's one of these variables that you can change and see what happens. But we'll start by setting that to 5. What we're going to do here is our X matrix will be an extraction out of xall. We will randomly sample 5 of the 1,440 features that we have here. So that now we have Y are the ages and X is a matrix with 1,004 rows for 1,004 subjects and 5 columns only. I can actually, I'll add, if I type Control-MA, that adds another cell right above where I am, and I use that a lot because it lets me do things before I do things. So here is X and here is Y. Good. Okay, let's use scikit-learn here. The first thing that we'll use is an object called linear regression. Linear regression, per default, implements ordinary least squares regression. You saw me implement that by hand using NumPy before. Inside of this linear regression object, somewhere something like that is happening. The API is a little funny when you first see it. There's an object here, and I'm initializing it with no inputs whatsoever. And so now I have this object, it's a model, and it's just sitting there. I haven't even shown it the data yet. It's just sitting there, notionally waiting for some data to show up. And it knows what to do once it sees data, but it hasn't done any of that yet. Let's look at this object model. Oh, I haven't run this code, so I don't have there it is, linear regression. It's this object sitting there. In order for that model to change, to adapt to data from the environment, we need to call the first of the methods that's very common here, which is fit. And when we give it an X and a Y that are formed in the way that scikit-learn objects expect, it will now fit that. And now this model object has adapted to this data, and it's changed such that it is able to do, well, it's learned something about the data. So it's assumed some parameters. per default, linear regression, when you don't tell it anything, it will estimate an offset. Remember that I have that additional parameter that I added. Per default, linear regression in scikit-learn will add that column of ones to the X matrix so that it can estimate an offset. And so that's this intercept. Where is it? This intercept here is that thing, and we're rounding it to 2 digits. And then these coefficients are one coefficient for each column of the X matrix. So there are 5 of those here. And they vary dramatically in size. And you can see there are really small numbers here. There's things that are basically 0 and some that are larger. And at this point, we shouldn't make too much of that. Remember that there are several different properties of each brain area, things like the area of the brain region, or the thickness, and I think there's curvature, and those are in very different units. So this might be just the scaling issue, like the variance of these 5 different columns that we selected are really, really different. So we haven't done any scaling here. So this might be just that. Yeah, and that's just what's written there. Let's see, there's a question back there.
Yeah, I guess I was actually going to ask a question about scaling and whether you think there are any best practices in terms of like centering or is this scoring specific types of data for
Yes. Yeah, I think scaling, I mean, usually when we deal with data that has these kinds of properties, we tend to do standard scaling, basically into z-scores, essentially. Yeah, which seems reasonable to do, but depends a lot on the details of what you're trying to do. In general, again, this is an empirical question. You could, in the setting of machine learning, you'll see how to do experiments later. You can try it with scaling, try it without scaling, see where you predict the age better, and go with that. So, and that's going to be my recurring answer to everything. So I'll come back here just to kind of emphasize something. When I initialize the object here, if I were to ask, what is the intercept? So again, now I've overwritten the model. Just this is important. I've overwritten the model, the name model with a newly initialized model object that hasn't seen any data. At this point, it doesn't have any intercept. The scikit-learn very helpfully adds this underscore at the end of names of variables that are only initialized inside the object once it's seen some data. So now it does have an intercept. Now it's seen some data, now it has this. So there are attributes of the object that only get set at fit time. And helpfully, these objects also have a model that is fitted, I think, now maybe it's, never mind, I don't know what it's called. But there's a way to figure out whether the thing has been fitted. Maybe it's a method. No ways, never mind. Ignore me. But anyway, there are, it's not too important for our purpose right now. If there are these underscore variables, that means that the model has seen data. And those only get set when the thing is fitted. Okay. I've emphasized how important prediction is, and the next thing that we can do once we fit one of these models is to use it for prediction. And so these objects have these estimators from scikit-learn also have a predict method, and the predict method takes as input only an x, only the x, and the thing that they produce is a set of y's. So this is the inversion of the model. We've shown it x and y together. That's the supervised learning part. Now we're giving it only x and asking it to produce an estimate of y or a prediction of y, and it produces a set of labels. And we can visualize that over here. Here on the x-axis is the predicted age from the model, and on the y-axis is the true age. And we can look at this and think, is this a good prediction? Is it not a good prediction? When does it fail? How does it fail? Clearly it captures some of the variance, right? You could put a straight line through here and try to show how well it does, and we'll talk about quantifying that in a second. But clearly it misses some things, like there are people who are 60 years old in the true, and this only goes up to 30. There are various things that are happening here. But just stepping back a little bit, it's kind of cool. We with only very few lines of code, we've taken some data, we've fit a model, and now we're making predictions about people's age based on brain data. So that's pretty neat. Here it is. Here's the whole thing. We initialize the model up here, then we fit it to some data, and then we create a prediction.
Are we sure if you, I think it's noticeable in there.
Oh, what error did you get?
Yes, the join slot takes from 0 to 1 positional arguments, but 2 were given.
Yeah, we have like a discrepancy with, I think, your code in the line above to the flag.
So maybe you just add a second.
Okay, this thing.
The X, Y, red, that's missing.
Oh, no. Okay, I may have made that change and not committed it. Could be.
So you just add an X.
Sorry, I'll put this in Slack so it's
There we go.
I'm not sure.
that should create this. Does that work now? It works. Okay. Okay, so just to come back to the big reveal here is this is all we had to do once we have X and Y in the right place. This is all we had to do in order to fit the model, initialize the model, fit the model, and then predict from that model, make predictions. So that's a neat API right there. And again, to make a distinction from sort of traditional statistical inference, we're not necessarily all that interested in these parameters. As I mentioned, they're limited anyway because of the scaling issues. We were really interested in, did we create a system here that systematically, well, there's a little side here. You could do that if you wanted to, because there's stats models as a library in Python that does this kind of traditional statistical inference. And here we're fitting in ordinary least squares, and you get all the nice things like adjusted R squared and an F statistic and p-values and whatever you want. But that's not what we're up to here. Instead, we want to quantify how well did we predict in some well-defined way. We'll go to that next, which is to quantify how well was this prediction working. One way to estimate performance of a model uses a quantity called the coefficient of determination. In scikit-learn, that's implemented inside of a metrics module as the R2 score function. So if I'm predicting here, I can take the true value, I can take the predicted value, and I can compare them using this R2 score. And that gives me a value that is bounded on the high end by 1. And if it's 1, that is it basically means these Ys are all identical to these predicted Ys. And that's usually a good thing for a model to be really, really accurate in this prediction. This number is bounded on the bottom by -infinity. And that often confuses people because it's an R squared. How could that be a negative number? And it's important to make a distinction between this number and the Pearson correlation coefficient, which is in fact a squared value and is between 0 and 1, just to say that this number is not really a squared number. It roughly corresponds to the proportion of variance explained when it's between 0 and 1. But you can imagine, because of the way that it's calculated, it quantifies model error relative to a baseline model, where the baseline model is what would happen if I predicted always the average in this data set. And if you always predict the average in the data set, if your Y prediction was, I'll just do that here. I think this will work. Whoops, no, that doesn't work at all. No, I need to do some broadcasting. Okay, I'll do that because that work. Then it's 0. So 0 is exactly the performance of the model that is a baseline that predicts the average of the data set. And you can easily contrive a model that's worse than that. And that model, like for example, just predict that everybody's 1,000 years old. And that model will be worse than this model. And that model will have negative R squared. Let's do that. indeed, it's worse than the mean model. So the way to think about this model is that it is about the explained variance. It's a proportion of explained variance. And at the very worst, you can say, well, we're not explaining any variance because we're always predicting the mean. And that's zero explained variance. And we could do worse than that. And we often will. For various failure modes. So when this comes back negative, it's not that the calculation is wrong, it's something is badly wrong with your model. Okay. So that's the coefficient of determination. It's often used. It's nice because it's on a similar scale, regardless of the scale of the data. Another kind of measure you could look at is the things like the mean squared error or root mean squared error in the prediction, but those have their own benefits. Those depend on the scale of the measurement, and the nice thing about them, they come back in units of the original measurement. So if we were to calculate the root mean squared error here, it would come back to us in number of years, which is a nice way to quantify how good a model that predicts age is, because we understand what years are, and we have a good sense of like this predicting, like if you wanted to say, is this good performance or bad performance? If I told you, well, it misses by on average 10 years, then you could say, well, that's not so great if I really, really need to know if that person is, 11 or 12. But if I only care roughly a decade, then that's actually a fine model. And R squared doesn't tell us that in units. Instead, it tells us in this fairly opaque R squared or variance explained kind of thing. Nice thing is we can compare different things, apples and oranges, or years and parts per million of some molecule. They all can be compared using R squared. So those are sort of the trade-offs of different kinds of scoring mechanisms. I'll just point out the API, the scikit-learn, also provides a method. Once you fit, you can score a model. And by default, the scoring model for a lot of these linear regression kinds of models, we'll see more of those in a little bit. Per default, their scoring is the R squared metric. So let me pause here for a second. What questions do people have so far about scikit-learn API, about estimating these models and quantifying their performance? I'm considering whether even to do this classification. Let me actually skip over classification. If you want to look at classification, look at this section. It's a little bit of a deviation from our main topic here. So I'll just point out, you can do classification. The API is remarkably similar. You import from somewhere else in scikit-learn, you import an object, in this case called Gaussian NB for Gaussian naive Bayes classifier, and your Y now, instead of being the age, is the group, autism, yes, no, and then you fit it with a fit method, and you score it with a score method, and so on. So probably similar to regression or classification, but I'll skip all this about how to quantify that, and instead go down here to ask, well, are we happy now? I'll just start running this code here because it takes a little while to run, and then I'll tell you what we're doing. So okay, so far what we've done is we've taken some data and we chose at random 5 features from that data, and we fit a model that seems to predict 20% of the variance in age among individuals. And that seems interesting and kind of remarkable. Now, instead of doing that, what I'm going to do is I'm going to fit with increasing numbers of features. And I'm going to run 10 iterations, or I am running currently 10 iterations of this linear regression. And I'm going to score. And once I do that, I'm going to plot a plot that has on the x-axis the number of features that have been selected, and on the y-axis the performance of this linear regression as the number of features included in the model increases. And I guess my question to you all, once this is has completed, what will this line look like in your estimation? It's going to be flat, monotonically decreasing, monotonically increasing. What kind of values will it take? What's your guess? Will it ever be negative? Any guesses before it shows up? Yes.
Will increase next to the features, but at some point flatten out.
So you are correct. It will increase as we add more and more features, which is we're providing more and more information to the algorithm. Where do you think it will flatten out? At what value? What's going to be its maximal value roughly? And what will that depend on? The answer will show up here pretty soon, I think. Maybe it'll show up soon. If it doesn't show up soon, then I'll make it show up soon by going to a static version of this. So this, I'll give you the answer since this is taking a long time. I'll just pull up another version of this picture that I have in this book that Tal and I wrote that has this is it in here? It might be in here somewhere. Either it's in here or it's in the next one. There it is. Okay, so this is what the curve looks like in the end. X-axis number of brain features used, y-axis performance, and it is indeed monotonically increasing. And then at the top, it just goes to 1. And the kind of important concept to grasp here is the title of this chapter, overfitting, which is the fact that in all that we've done so far, we've used the same data. Oh, here's the curve. We use the same data to fit the model and to evaluate it. Given enough features, the model will actually fit perfectly well because it has so many degrees of freedom that it can capture all of the variance in the data. So there are 1,000 observations here, 1,004 observations, and given 1,440 features, you can basically fit a model that passes through every single point in the data, if that makes sense. That is not super intuitive because you think about this, like in my head, I'm thinking about linear models, right? In 2 dimensions, it's a straight line. Now I can expand the number of dimensions to like 2 dimensions. Now I'm thinking about a surface. Now go to 4 dimensions, it becomes a surface in 3 dimensions, some kind of hypersurface. And here I am in 1,440 dimensions with a 1,440 dimensional hypersurface. And how does that thing pass through every single point in the data? To me, it's a little bit confusing, but 1,440 dimensions, who knows? It's very high dimension. Another way to think about this is to then instead think about overfitting, which is to think about the degrees of freedom of a model and how those degrees of freedom relate to how it overfits / underfits some data. So instead of thinking about this really high dimensional data, we're going to instead think about models with more or less degrees of freedom in something that we can visualize. So that's the thing that we're going to do next. But actually, before that, just well, let me go to that, and then we'll come back to this figure and try to understand it really. So here I am in this notebook number 3 called overfitting, and what we're going to do here is we'll still use a linear regression model, and we're going to make some data. Again, this data will have one feature in X and one feature in Y, and that's useful because we can visualize that very easily. The model this time, you remember last time I simulated a model, it was a linear model, a linear relationship between X and Y. Now it's a slightly more interesting relationship. It's a quadratic relationship. So we got a quadratic term here, and then we got a linear term here, and then we got some noise over here, and we're going to create 30 points out of that. So here's again, X on the X-axis, Y on the Y-axis, and let's try fitting that with the linear model. We've done that before, so here we are doing that again. With scikit-learn, we initialize the scikit-learn linear regression model. We do something slightly funny here, and that's because scikit-learn expects a 2-dimensional input for X, and Rx in this case is 1-dimensional. And this is a way to take a NumPy array that has 1 dimension, add 1 dimension to it in the end by indexing with none on the 2nd dimension. And then we are going to plot the result of that. We fit that and then plot the result. And we also write down the mean squared error. So this is the fit of a linear model to this data. And It's not great. It's capturing some of the data, but there are obviously things that it's getting wrong. And this is a case of what we call underfitting. The model is not flexible enough to capture all of the ways in which the data varies across the range of values that has been provided. So what we're going to do now is we're going to incrementally add more and more flexibility to this model. The way that we're going to do that is by using what are called polynomial features. So if you have a series X, you can add next to that the series X squared and X to the third and X to the fourth. Those are called polynomial features of X. So we're going to fit a model it's a linear model, but it's linear in polynomial expansions of the X value here. So so each one of these points is going to appear in X multiple times, and it's X to the one value, X to the squared value, third, and so on. And those are called polynomial features, and scikit-learn implements those because polynomial regression is a very useful thing generally. Another thing that we're going to introduce here are scikit-learn pipelines. Pipelines are very, very useful. The idea behind pipelines is that sometimes when you're fitting machine learning models, you're doing multiple steps. In this case, we're doing the pre-processing. We're taking X and expanding it in this polynomial into these polynomial features. So that's a pre-processing step that we might do with the data. But you can imagine doing other steps like normalizing and doing some dimensionality reduction. And all of those things together should be kind of done together. I think Russ showed in his talk kind of the worst case where you're doing feature selection outside of your cross-validation loop, and then you end up getting grants of millions of dollars and publications in high-impact journals that are based on error. But one way to avoid that is to pack all your stuff into a pipeline. So scikit-learn, in addition to all its benefits, the API is one that if you use it to its full extent, will prevent you from making errors that will just kill that high-impact paper in its youth and prevent you from getting millions of dollars from the NIH. But at the same time, will prevent you from making some pretty basic errors in machine learning. So the way that the pipeline object works is that you give it steps that you're going to do in your pipeline. Here we're implementing a function that makes the pipeline object for you. You give it a degree, and then it expands the polynomial features up to that degree, and whether or not to include bias in there. And then what you're doing here is your pipeline includes first the polynomial features and then the linear regression. So it's going to expand the polynomial features for every X, and then it's going to fit them all with that. Okay, here we're fitting a model with degree 10. And lo and behold, the mean squared error is really low, much lower than here, and it's captured a lot of the squiggles in the data. But this is the kind of thing that makes it clear why additional flexibility of the model might be not that great. And here, instead of in the 14 and 40 dimensional case, you can see why the model can fit every point. If we added enough of these polynomial features, you'd have the polynomial expansion here just go through every single point. Here it's bending itself way out here so it can fit this one point that happens to be way over the point. So this is clearly a case of overfitting. What do we mean by overfitting? In this case, it has a very technical sense, which means that if I were to generate another data set randomly from the same process that generated this data, it wouldn't fit that well. It would be fit very well to this, what we call training data. But taking the same model, this same line, and comparing it now to data generated from the same process independently would just perform terribly. And we can demonstrate that here. So I've run again the data generating thing. I've taken the same line, and you can see that it's really, really terrible. It's worse than the linear model, it's worse than the other fitting. And that's because it's still stretching itself way up here to fit that one point that it had incidentally had in that case. And so this is really the reason that this also happens here is we're in this setting where this hyperdimensional surface with a lot of more dimensions than observations can just pass through every single point in the data. If you have enough dimensions, you can do that. But this is more clear maybe because it's in the two-dimensional setting. So the Goldilocks principle applies here just right? So here we're creating a pipeline, we're creating the pipeline again. Now we've used the second order polynomials, our highest order of polynomials. And we can play around with that. There's a little widget here. You can play around with lots of adding. And in this case, we're generating separately training and test sample. Okay, so that's overfitting. And I should start going faster here because we've got 30 minutes left. What questions do people have at this point about this overfitting idea? Right. Yes.
Is the idea that you would take your fit based off of doing a number of polynomial features, or do you just like see what helps again?
Yeah, so we'll come back to this. I'll talk about how to ground this all now, and then we'll talk about this is the whole topic of model selection, which is how do I know how many degrees my polynomial should be? I'll show that in a slightly different setting, but the answer will always be the same. You create an experimental design that allows you to evaluate your model without overfitting, and then you select based on that. And so this is going to be the topic of this notebook, which is how do we design an experiment such that we're not overfitting. The principle is very simple, and I'll just state it up front. The method that we'll use is called cross-validation, and it's really what happened at the end of that notebook, which is that you train your model on some data, and then you test your model on another set of data that was generated from the same process, and but doesn't have the same noise. The problem with overfitting really is that when we are doing something like this, we're fitting both a pattern that truly is in the data, and given enough degrees of freedom, we are also matching the noise that is in this data. Now, if we were to take two separate samples generated from the same process, those have, by the definition of noise, they have separate instances of noise. And so if we fit to the noise in one data, that wouldn't work very well on the other set of data. But if we fit just right, just to the signal and not to the noise, then we're right in the sweet spot. So let's see how we do that. Again, we're going to read in the abide2 data set. We're going to take this X all and the age. So we're doing age regression or age prediction again. And now we're going to use a neat little function called train test split that takes and splits the data by rows. So what this does is it receives two arrays in this case. It can receive more arrays if you want. And then it, because we said the train size should be 0.5, it splits each one of these arrays, both the Y and the X, into two equally sized, in this case, but that will depend on this input. Equally sized arrays, same number of rows in each one, 502 rows in the X train and 502 rows in X test, randomly selected from here. So it's not just taking the top half and the bottom half, it's randomly selecting rows and assigning them each to X train and X test. And importantly, and very helpfully, it's taking the same rows for Y train and Y test. So Y train and X train are still matched row by row. The first value in Y train is the same subject as the first row in X train, and an X test is just a separate thing. And indeed 502 by 1440. And then what we do down here is that we're going to perform cross-validation. We're going to initialize a linear regression, going to fit that, and then we're going to estimate two R-squares. One is done with X train and one train, and the other R-squared is done with the X test and Y test. Now, on fitting, this data only saw the training data. This model only saw the training data. On estimation, it's seeing both. So or on scoring, it's seeing both. So down here, it's not adjusting its behavior. It's just doing an evaluation. That's really important. And we'll give you this thing here. So similar to the curve that we saw down here, it's fitting perfectly in the training sample. And lo and behold, it's got a negative R-squared. It's doing worse than the mean model in the test sample, and that's because it's severely overfit. Okay. What if we instead sampled 200 features here? What would happen then? Well, now the situation is actually not as bad, interestingly. We're still, the R squared in the training sample is still high and positive. It's not 1 anymore. It's not perfect. And that's because we didn't take, there, as I said, there's 500 samples in this training data, and we have less than 500 features that we've selected here. So we're not fitting perfectly. And, you know, in the test sample, we're actually not doing too bad here in this case. So that's interesting. We've taken less features and now our model is in some sense better, which is an interesting. And of course, the question that you asked before is like, well, how do we know 200 or 500 or what exactly we're supposed to do? And we'll get to that in the model selection, how to do this more systematically. Now, one thing here that's also a little odd is that we've kind of arbitrarily chosen some data to be training data, some data to be test data. There's a more systematic way of doing this, which is to split our data into training and test sets n times or k times and repeat this process k times. So here is the schematically from an image taken from that blog post there. It is in the first iteration, we leave out, I don't know, in this case, we're doing 10 iterations. So 10% of the data, fit them all to 90% of the data and test on this left out 10%. Then we take and we sample some other 10% and so on. And so in every iteration here, overall, in all iterations together, every single observation in the data has been in the test data at some point. So you have a set of predictions for every individual in the data set that are based on a model that was fit when that individual was not in the training data. So you can actually evaluate all these left out things against the real data. And that'll be an evaluation of the prediction of models that are all fit without the, so not overfit. And that's a way to evaluate. Another way to evaluate is to calculate an error in each iteration, or an R squared in each iteration, average those. That's also quite commonly done. I actually won't show this here. We programmed this very, very explicitly, how to do k-fold by choosing indices and stuff like that. But let's just do it the easy way here. There is a function in scikit-learn called cross-val score that will do the whole thing for you. You tell it, I want 5-fold cross-validation, and I want this done with this estimator, this linear regression estimator. You passed it the estimator, you passed it some data, X and Y, and you tell it how many folds you want to do, and it will do all of that under the hood. It will split it into 5, it will do those left out. In this case, if you do 5, then you have 80% of the data is each time in the training data, 20% is in the test data, and you get 5 R squares down there that are all R squares, cross-validated R squares. These R squares represent an estimation of the model fit quality that doesn't depend on overfit. It's not overfit. This is a good estimate. Yes. Yeah.
Yeah,
Go ahead.
there's a question. So if I wanted to do like leave one out for validation, I would just make k the amount of subjects and the amount of
Yeah, and there are other functions in scikit-learn that let you do leave one out. Yeah, leave one out is when the number k is equal to the number of subjects. So each subject is left out in a separate model. Okay, and there's ways to sort of get deeper into this. There are different APIs, including this one is very straightforward. It's a functional API that lets you do this directly, but you can also program this a little bit more subtly. I'll just mention one of the advantages of the pipeline objects is that it lets you, if you had a pipeline, you could pass the pipeline here as the estimator. Pipelines have a fit method, just like an estimator on which the pipeline is based. And so that's really nice. If you're doing several steps, you want it to be done all together. You want to separate all of the steps of the pipeline. The model, the feature selection, these polynomial features, if you're doing dimensionality reduction, all of those things have to happen separately for the trained data from the test data. If you pack it all into a pipeline, pass it in here, then it will naturally do that for you, which is really great. So I highly recommend pipelines. Okay. The next one here is called cross-validation as a panacea. It's optional. I'll just point it out. this is really remarkable. We're doing really well here at predicting the age of individuals based on some randomly selected 200 features from FreeSurfer. What is still really fishy here? What could we still be doing really wrong? We've done cross-validation, so we're not overfitting, but still some way that this could really go wrong. Yes.
We don't know what relevance the features we selected have to the data.
Yeah, so we don't know, and we could go and look at the relevance. These are linear models, so there are coefficients on that. And the coefficients, if we scale properly and so on, those coefficients actually tell us this feature is more important for this than others. We can kind of read those out from the linear model because under all of this, there is an equation which is, age equals some offset plus beta 1 times this feature, beta 2 times this feature. And these betas, their relative size once the features are scaled up, it's kind of relevant. It tells us their relative contribution. So that's one thing. But what is still where could we still be really severely fooling ourselves here? Yes.
Is it multicollinearity?
Multicollinearity is an issue here, although multicollinearity should only hurt us. Multicollinearity is the fact that maybe some of these features are related to each other. They're linearly related to each other. And that's a problem when you're doing estimation of these beta features and beta coefficients, whether they're statistically significant, and that might be a problem in that setting. Here, if they're multicollinear, it should only hurt us in prediction, and apparently it's not hurting us in prediction. So we should be doing great, or we shouldn't be doing this great, but we still are. Yes.
And to be completely wrong, but could it be that one of the individual full scores is higher than the R adjusted R square that is below?
Say that again.
That one of the individual full scores is higher than the mean corresponding R.
Yeah, so the question here is just to notice that there's some variance among these R squared. It's just one of them is somewhat higher than the others. And that is one of the reasons that we do this. We don't want to capitalize on chance, on the fact that we selected some really great test data and trained data in some case, but is actually ultimately is fine so long as we average across all these properly and maybe do some additional checks. I'll tell you what's going on wrong here, which is actually not in the machine learning part at all. It's in sort of our scientific thinking about this. And that's the fact that if we look at the age distribution across sites in this data set, it's widely distributed. So, these are the sites, and each point here is a subject, and the y-axis here is the age of the site. So if we know which site this person is from, based on their MR images, we can guess their age really accurately. And in fact, that age residual that was in that table, that's each person's age once you remove the mean age in their site. And if you use that instead, I have sad news for you. Selecting 200 random features of their brain is unfortunately not going to predict their age very accurately. So you need to do something more. So should we just give up now and call it a day? It's late. Perhaps that is not a bad idea. But maybe let's push on just a little bit more. I'm actually not going to go into these learning curves. They're nice. They're really great facilities within scikit-learn that I encourage you to learn about, that let you sort of do these experiments about what and how should you include more data, less data. How is are your models affected by different kinds of different settings? I will just point out one more thing is that if you are starting to do lots of experiments where, for example, here we randomly selected 200 features. There are a lot of random groups of 200 features that we could have selected, and maybe we should try another set of 200 features and do this again and repeat that experiment, I don't know, as many times as we can select 200 random features. And then ultimately, if we do that enough, we will randomly fall on a setting where even with cross-validation, we just randomly select some 200 features where this happens to work well, even if we've residualized out the site and so on. And so you can do these experiments a lot, and you can, that's the paper again, I think Russ showed that in his talk. I tried a bunch of things. Even if you use cross-validation, if you try enough things, you will find a particular setting of your hyperparameters of the model. These models can get really complicated. That just kind of works really beautifully, and you're still fooling yourself. And the way to know that you're not fooling yourself is to use a slightly more elaborate mode of cross-validation, which is to say you lock away some data first. You call that your true test data. This is going to be your true check on whether what you're doing makes sense. Then you take your trained data and you do whatever you want with that trained data, really, whatever you want. I mean, you'll develop over time, and we'll talk about some strategies in just a minute here, ways to do this that make sense, right? Experiments that make sense. But in principle, you could do any permutation of anything you want in here until you're happy and satisfied and think, oh, I've hit the right algorithm. Now you take and you apply that algorithm to all of your training data to predict that test data. And that evaluation of that test data is a good and accurate estimate of how good this model really is. Not all these evaluations that you've done here, because you can repeat these evaluations until you just hit the exact right mode of that where you're really just overfitting. Again, overfitting to some weird combination of hyperparameters, train and test data, splits, and so on. So this is, you have to do this when you do machine.
Any sort of feature selection or estimation and parameter estimation would happen after the validations, right?
Yes, all the hyperparameter estimation, so there's sort of settings of what exactly what algorithm you use. There are many algorithms you could use to fit the data. Some of them are linear, some of them are nonlinear. Things like how many polynomials you select, which of the features you selected, and so on. All that needs to happen here. And then you fix all those things, and then you take that model where you fixed, which features you selected, or at least the strategy used for selecting the features, the number of polynomials you're using, all that hyperparameter setting. You fix all that, you fit it one last time on all the training data, or maybe you fix it all over here. Anyway, you generate using this data and only this data, some strategy to predict on some truly unseen data. And then you take that data that is truly unseen and you test it on that. And then if you're accurate there, then I'll believe you. Yes.
I have a question. Since you're splitting these test and train, and what you could be doing in the train is picking up some distributional properties of the sampling characteristics, etc. And since it's random, the distribution should still be relatively similar in the test. So could you still be tricking yourself when you?
So there's in that question, I think there's multiple things. One is about, could I be picking up something that is still noise in that test data? And there I'll say probably not, because the noises are supposed to be, a noise as defined as noise is something that's independently sampled for these two groups. It's for every individual. It's like a, identically distributed independent sample of noise that has been associated with that measurement somehow, right? You could still be picking up what you were saying about some distributional properties of the sample from which this whole group came. And then your problem is really generalization to some other group of people, right? Whether or not you can make inferences about the general population from which this data came is another problem, right? You might still have, for example, you may have a limited set of socioeconomic status within this sample that you're working with, or somebody mentioned just kind of racial distributions. There's some really nice papers recently about just how things go wrong when you transfer for samples that have worse representation of different racial groups to samples that have better representation of racial groups, and how these kinds of methods fail there. So there's still conceptual issues that you'll have to deal with. But in the statistical sense, this model evaluation is not overfit, at least to this particular distribution. Does that answer your question? Yeah.
Does mine that with like stratified sampling when you do test help with that?
Yeah, so it's a good idea, even from the model fit accuracy kind of improving prediction, to stratify. For example, if you have different age groups within this, or different sex is often a thing that you need to stratify on because of differences in between male and female subjects in your data. If you stratify on that, that should improve your model prediction. if your training data for some reason has only young individuals and your test data for some reason only has older individuals, you're gonna fail because of that. So that should help. Stratifying in advance on the relevant parameters or relevant variables is going to be important. Okay, let me actually move on to model selection. We can continue the discussions about these things later on. Just I want to make sure that I get to this point where I give you a little bit of an experimental strategy to work with this within this paradigm. So again, we're going to read the biodata, and we're going to talk about how to systematically trade off between overfitting and underfitting. And in order to talk about that, we need to talk about bias and variance. Well-known fact in machine learning is that error can come from two different kinds of sources. So imagine for a second that we have all these samples here, and the true value for all of these samples is the thing right at the middle of the dartboard. And to the extent that any point here is away from the center of the dartboard, that's an error. And generally speaking, when we're designing a machine learning model, we can have two sources or two kinds of settings here. This is the best setting. There's not a lot of variance in how much, where we estimate each point is. And there's not a lot of bias. They're all centered on the center of the scheme. We could also have a low variance situation where all these things that should be very similar are very similar, but they're all biased. It's all away from the center. And that incurs some error. But there's also another setting that could cause error, and that's that things that should be the same are all getting different values. And that's a high variance, even if low bias. So this cloud of points and this cloud of points in total could have the same amount of error, but for different reasons. In one case, the model is biased, it doesn't quite, it's not centered on the right place. In another, it's centered on the right place, but it estimates different things for different people. And this, of course, is the worst case scenario where variance and bias are both high. And it turns out that you can trade off those two things. So you can design algorithms that add bias to your estimation and also remove variance. And if you find just the right amount of bias to add that will reduce the variance enough, you might actually get to a situation where you have lower error in total. And that's a trick that's very general. So this is the conceptual picture. Now I'll show you how that's implemented in truth. I'll skip over this little allegory about parking lots and let you read that separately and just go to the meat of the method itself. And this is the general topic here is called regularized regression. The idea is that regularization is a way to impose some kind of preconceived notion on the results that a regression algorithm gives you. And by doing that, you're adding bias to the results that you're getting and potentially reducing the variance enough in order to actually get less error overall. How is that done in practice? Let's look in the details of what the ordinary least squares algorithm, and I apologize for math in the 10 last minutes of a very long day, but let's look at what ordinary least squares does, and I'll unpack this. What ordinary least squares does is it reduces the squared error or residual sum of squares. What is that? I have a prediction of a specific y, a y for a specific individual. That's this thing here, beta j times xi, sum over p, all the parameters of beta j xij. That's my estimate of y, or my predicted y for individual I, and then this is their true value. I take the difference between that and I square that, and I sum that over all the individuals, and that's the residual sum of squares. And ordinary least squares tries to reduce that as much as possible. And that's how these hypersurfaces in 1440 dimensions come about, is by trying to find the set of parameters that reduces this as much as possible. Now consider a slight variation on that. Consider an algorithm that does that, but also at the same time, try to reduce as much as possible the sum of the absolute value of the coefficients, these betas. So it tries to find somehow, if you think about this hypersurface, a hypersurface that is as flat as possible in 1440 dimensions. One that has as small as possible sum squared, sum of the beta coefficients. We'll come to sum of squares in a second. And then you add a lambda in front of here, which is a hyperparameter, that tells you how much you're going to relatively weight this new penalty that we've added, we call this the L1 penalty, which is the absolute value of the sum of the absolute value of the coefficients, and how much we're weighting the residual sum of squares. And this is called the lasso, or an algorithm that does this is called the lasso. Another algorithm we might use, or another kind of penalty we might use, is one where we're penalizing, instead of the sum of the absolute values of the betas, we're penalizing the sum of the square of the values. That's slightly different, but has a similar flavor. In both cases, we're adding some bias here, and we're hoping that we're reducing variance enough in order to overcome, in order to benefit from this bias variance trade-off that we talked about. Let me show you what that looks like. And given the time, I'm not going to talk about every detail in the code here, but I am going to explain the graphic at least here. So we're doing the same thing that we did before. This is age regression. We've sampled 200 random features from the abide data. It's still subject to all the issues of the sites and so on, but we're just going to swallow that here for the case, for the sake of the demonstration. This takes a little while to run because it's running over multiple values of this lambda parameter, also called alpha in the code here, just to confuse you all. In scikit-learn, it's called alpha. I think it's because lambda is already taken by Python for other things, or maybe because in some papers it's written as alpha. Anyway, each point here on the x-axis is a different value of this penalty. And what I'd like you to observe is that if this penalty is very, very high, and each line here is a different coefficient. There are 200 lines for the 200 features that we've selected. And the value on the y-axis is the value of the coefficient. And so some values are negative, some values are positive, some features predict age positively, some predict age negatively. But over here on the left side, the sum of the absolute values of these things is relatively large. And over here, we've set alpha, this penalty parameter, hyperparameter over here, to be so high that we're just penalizing over that, and we're basically ignoring the residual sum of squares. And this is just going to go, the coefficient is just going to go to 0. That's lasso. We can do a similar thing for ridge. And then the question is, how do we select among these things? And the answer is what we saw before, which is we do cross-validation. So here what we're going to do is we're going to run a full cross-validation setting. We're going to select an alpha from among a whole set of alphas here. This is this X range. And we're going to run a cross-validation experiment with that setting of alpha, such that now we're going to plot the R squared for different values of this alpha. This might take a little while, but hopefully the principle will be clear in just a second. The idea is we're selecting the level of this regularization, the level of alpha that we want to select based on an empirical evaluation in a cross-validation setting. And this is really in some sense, this is the last figure that I need to show you today, which is to say, we've used lasso, this algorithm that restricts the dimensionality of the model, effective dimensionality of the model. It restricts the variance that the model is allowed by introducing a little bit of bias. And what we can observe is that in the trained data, the R squared that we evaluate in the trained data every time, that keeps going down. And that's because the model is moving further and further away from the solution that is the best residual sum of squares in the training data. But in the test data, well, we start here very close to where we would have been with ordinary least squares regression. We're comparing all the time to ordinary least squares regression. And that's because in this setting, it's really very close to the residual sum of squares best solution. There is a point at which the penalty is sufficiently high to actually improve over ordinary least squares. And then, of course, at some point, it just crashes. It goes down to 0 down here. And you can think about that and about how we defined R squared later on, because over here, all the coefficients are 0, except for the offset. So we only estimate the mean. That's the reason this crashes to 0 in the end, because the model over here is really just guessing the mean of the data. So that's why it ends up at 0. But over here, somewhere, there's a right level of this penalty. And if we were doing this experiment for real and we had separated, like I said, the test data separately and done this internally and thought this is a really good model to use, we would have gone here and said, this is the right setting of alpha for us. Let us decide on that, fit it to the whole data, and then evaluate it on this left out test data. And this, in a nutshell, is a lot of what we do with machine learning. We do these experiments where we can try this, the same thing can be done with ridge regression, which is this, the penalty now is the sum of the beta squared, not the sum of the absolute values. And you can go and you can compare in this cross-validation experiment, did ridge do better in this setting than lasso? So it's not only about setting the hyperparameter for a particular model, you can compare across different models and say, is this R squared, that is the best R squared for ridge, is it better than the best R squared that I got from lasso? And select the model that we will use. And later on this notebook, there's also other nonlinear models. So you can do a whole thing there. So long as you're not fooling yourself, so long as you're going back and doing something like this so that you don't try a bunch of things and then just conclude conclusions that are incorrect. But that's, generally speaking, that is sort of the setting in which we work with machine learning. I think you'll see more examples of this kind of experiment with more interesting data tomorrow. But let me just see what questions you have at this point. That was a little quick through the regularization in the end, so I'm happy to talk through that more, say on Friday, the review. Well, let me take questions here. Yes.
I have the figure that's like later on the scikit-learn like flow chart.
Oh, this one.
Like I've seen that before and
Yeah.
just, I guess a question to get your opinion on, like, right after the start, greater than 50 samples, go ahead, less than that, get more data. I think like in our field, like this usually.
That's where you stop. Well, not exactly, not for all data sets, but yeah, I mean, there's a real balance between the number of rows in a matrix and the number of, we are often working in in the setting of very, very wide matrices that are very shallow. Even in that bi data set that has 1,000 in some samples, we still have very wide matrix of 1,440 features. And that situation is often worse than that. So, and regularization, that's really the setting for which regularization techniques were sort of invented, this like wide, shallow matrix. You prefer to be in the transpose of that, if you can. Yeah, I should say this diagram, which is cool, which is a flowchart that tells you how to do machine learning. I think it started as Andy Mueller, somebody asking him, could you give me a flowchart, and him making this flowchart as a joke. And then he looked at it and he was like, actually, it kind of makes sense. So there are rules that you could follow.
When we're talking about samples in this, I know a lot of like big data studies are longitudinal, so then you get more samples, but then it's less, it's not like 10K per person. So how does like this work for time series data? Like, does the observation become a new sample, or do you just like have one person? Like, what's the best way to do that?
Yeah, we skipped the interesting part, right? The interesting part is how do you get from that three-dimensional MRI image to a table with features, right? And that's called feature engineering. And that's something like in my own research, I spend most of my time on feature engineering, which is I get like complicated, really time series, or in my case, the fusion MRI data. And the question is, how do we boil that down to a table with a reasonable number of features that are also the correct features that make anatomical sense, that make physiological sense? That's the science. After that, it becomes a machine learning problem. My observations so far is that part, the feature engineering, doing it like correctly is really, really important. You can end up with two feature engineering pipelines, one of which generates like 500,000 features and another generates on the order of 20,000 features. And those will perform the same in a machine learning setting. So you've reduced dimensionality a lot and you're still performing as well as a feature engineering pipeline that generates a lot of features. I know it doesn't necessarily solve the problem, but if it's a time series problem, for example, you might want to reduce it from a time series problem to one about which part of the brain likes which part of responds in which part of the time series, like which stimulus, right? That's the, and then work with that, right, with the beta coefficients. All right, cool. Thank you so much.